Okay, so we are.
Yeah, we are on. So
we are already on.
maybe we have 30, 36, 40.
39, 49, 54. Wow.
So once we reach 100, I will start.
It's going very fast. So 87, 94, 101. I will say that we can give
Did
like
I start?
maybe 2 minutes more, like, and then we 10:05 we start.
Okay.
137.
I think it's stabilized now. So should I start?
Okay, let's do it.
So welcome everyone to the workshop of what optical microscopy at COLife Friends, learning the basics. So in this workshop, we will cover the optical microscopy techniques and expertise available at COLife and at COOL. So as this workshop is divided in 6 webinars, 3 today and 3 on Thursday. And our first speaker of today is David Arcadi, head of the bioimaging facility at Champalimaud Research. And he will tell you about know your microscope, objective lenses, optical resolution, and sampling principle. Oh, I forgot to tell you, so if you have questions, you can add your questions to the Q&A, and they will be answered after the webinar. You also have the upvoting system. So if you see your question already asked, just click upvoting, and this question will be answered first.
Okay.
Okay.
So I guess it's my turn. Thank you very much, Marianne. I will share the screen now. So share, and you should see my presentation. Do you see? So guys, can you confirm? Okay. So welcome everybody. Thank you, Mariana, for the kind presentation. Today I will tell you about the importance of knowing your microscope, so your optical system. So in particular about objective lenses, and then we will talk about optical resolution and sampling principle. So we will start with a scheme of the epifluorescence microscope. So a microscope has also a bright field path, but we will ignore it in this moment, because the aim of this seminar, this webinar, is mostly a teaser, making understanding some of the basics, but also and specifically making understanding there is much more. So it's an invitation for your considerations, and then to ask us, and especially referring to your local expert or the team of experts present within the COLife project, right? So in the Lisbon and the Irish area. So in an epifluorescent microscope, so there are several elements, and we will need to have a look to all of them. And we will start with the light source. There are several, you should see my pointer. So there are several light sources. In this scheme, it's a mercury lamp, but it could be a laser, it could be an LED, it could be a xenon lamp, and so on. And then after the light source, there will be a set of optical elements and diaphragms that we will not mention in this moment. The second most important element that I would like that you took in consideration here is here in this position, in this scheme, where the light, that is a white light produced typically by a mercury lamp, changes in color from white to green, because this one is an excitation filter. So a filter that selects specifically the wavelength that we want to use to excite the fluorophores of our sample. This excitation light will bump into this optical element that is oriented at 45 degrees here, which is called main beam splitter or dichroic mirror, which will act as a full mirror for the excitation light, which will be directed downwards in this case. Will go through the objective lens, will be focused on the sample, which is missing in this scheme. The sample is an extremely important element of your optical system. And from the sample preparation, not only the mounting and the staining, but also, for example, the choice of the cover slip will so the quality of your images and the scientific information that you will retrieve might change. So then the objective your fluorophores will be excited, and when coming back to an energetic level that is called ground state, they will emit photons. These photons will be collected partially by the objective, so here, and will travel back upwards. And once encountering again the main beam splitter, since the emitter light is typically longer than the excitation light, they will pass through. After the main beam splitter, there is another optical element, which is the emission filter, which will further clean up the signal and make sure that only the signal of interest will reach your detector, that in this case could be your eyes, but it could be a camera, photomultiplier tubes, or there are many kinds of detectors. So any of these elements, this is very important, key message, any of these elements needs to have a webinar, actually like a full lesson with hands-on, okay? So this is not possible in these circumstances. So we will talk about only one of these elements, which is the objective, which is the prince, or actually the king element in your optical path, because everything in the microscope is made to support the function of the objective, okay? If your objective is dirty or damaged or simply incorrectly chosen, then the information that you will retrieve, the scientific information you will retrieve, might be compromised, right? So then, the first thing that we need to know about our objectives is that they are not simple lenses. So this is not like a cartoon. This is a real picture of an objective lens that was sewed into half. And you see that there are many optical elements inside of this an objective barrel. They are carefully aligned, and there are many mechanisms here that determine the positioning of each optical element with respect to the others. And this because each objective lens compensates for many aberrations. We will see the main aberrations during this seminar. Not only they are not simple, but there is a huge variety of objective lenses, and this is just like so there are of any flavors, many brands, many kinds. There is a huge variety even within the same brand and within the same magnification. So these are only Zeiss 20x objectives. So you see Zeiss and 20x, Zeiss 20x, Zeiss 20x, Zeiss 20x, and these are only 6 examples that I picked, because actually Zeiss offers 49 different 20x objectives. Now, clearly, these objectives are not all the same. So they have different characteristics, and they were made to answer to different scientific needs. So, but then, how do we navigate within this panorama of objectives? So how do we choose one? So let's learn together how to read and understand the characteristic of an objective lens. So this is a lens, and there are 2 pictures because one is the front and the other one is the back of the barrel of the same lens. So we can have access to the entire information. So the first thing that we need to read when observing an objective lens is the brand. So in this case, Zeiss. So don't underestimate the importance of the brand, because if you remember in the scheme that I quickly showed you before, so there are several optical elements inside of a microscope stand. Each brand engineers its own objectives accordingly to the optical elements that lens will find inside of the stand. Okay, so, and these elements might compensate for certain aberrations. They might be tuned at a certain distance to give a certain level of magnification, and there are differences between brands. So, for example, like Zeiss, they compensate for chromatic aberration inside of the stand, but they have different level of magnification inside. And then historically, Nikon and Olympus, they have like full compensation for chromatic aberration inside of the objective, and many other differences. So always couple an objective of a certain brand with the stand of the same brand, unless you truly know what you're doing. Okay. And then, if you go on and we move to the second line, we read there plan apochromat. So this line refers to the objective correction. So let's check first of all what plan means. So plan refers to the flatness of the field of view. So how explained in this cartoon here, on the left side you have the incoming light, and here we have our objective. So a flat objective, when imaged by a simple spherical lens, will produce an image that is not flat, but it's actually projected on a curved surface. Okay, so it's a curved image. Okay, so this implies that when, and it was like this historically in the microscopes, that having, when having the center of the field of view in focus, the border of the field of view were not in focus, and vice versa. So objectives that are instead like named with plan, they compensate for this and they correct for a large field of view. So then you see the whole field of view in focus in one go at the same time. Okay. Then if we move to apochromat, so this second term, or let's say the second part of this line where apochromat is, refers to the compensation of two main, or let's say correction of two main aberrations. These two main aberrations are chromatic aberration and spherical aberration. Before to go into the meaning of apochromat specifically, let's have a look what a chromatic and spherical aberration are and what they mean for our images. Okay, images. So, so this scheme refers to chromatic aberration. Again, we have the incoming light from the left of our screen, and then the white light here that enters this spherical simple lens, you will see will be divided in its components, and we have here the different wavelengths depicted as different colors. And the chromatic aberration implies that shorter wavelengths are focused closer to the lens with respect to longer wavelengths that are progressively focused farther and farther away from the lens. Okay, this causes in bright field images, for example, fringes, so there are colors fringes around the objectives, around the object. And I will show you here an image. On the left side, we have like an image, a bright field image of a grid that was acquired with an object that was not corrected for chromatic aberration. And on the right, the same grid acquired with an objective, that was corrected for chromatic aberration. So, and you see here these colorful fringes, and here they are known. By the way, these two images were taken from the movies Understanding the Light Microscope with Peter Evanet, which is available on YouTube. It's 1 hour and 20 minutes movie that I strongly recommend to everybody. It doesn't matter what is your level of knowledge of microscopy. These are beautiful movies. Peter Evanet is a senior microscopist of the Royal Microscopy Society. And he beautifully explains all the basics and the principle of light microscopy. So then, said this, it's important that you don't fall into the mistake that the chromatic aberration will affect only your bright field images and might not be really important if you do fluorescence. This is not true. In fact, the dispersion of the different wavelengths will be there even if you observe wavelength by wavelength. And when you are doing your multicolor experiment, your DAPI channel will be focused closer to your lens with respect to your GFP channel, then will be closer with respect to your cherry channel, and so on. So if you have a far right, will be still farther away. So consideration. The consideration is that if you are doing colocalization, you must know whether your objective is sufficiently compensating so for a chromatic shift or not, because otherwise, again, you risk to withdraw incorrect scientific conclusions, right? So, and in the worst cases, I saw papers sent back, and then so the reviewers asked to redo all the experiments because they were using the incorrect lenses for studying colocalization of subcellular structures. All right, let's pass to spherical aberration. In this scheme, again, we have on the left right hand here the incoming light. In this case, we are not considering different wavelengths, but we are considering one single wavelength that is filling the entire lens, okay? And the spherical aberration is caused by the fact that the rays of light, or the portion of light, let's say, that pass through the lens in the outer part, so that here in this scheme is let's say from 4 to 6, indicated from 4 to 6, will be focused closer to the lens with respect to the light and the rays of light that will pass through the central portion of the lens that will be focused farther away. So, and here are the rays that are so pointed with the numbers that go from 1 to 3. Okay. This means that if you have a single object, which could be your fluorophore, so for example, your GFP molecule, or any source point of light that emits light in every direction, and the light is collected by the entire lens, okay? So your single adimensional or spherical source point of light will be actually focused, or will create an image of a elongated object. So you see, oops, forgive me. So an elongated object that basically will not cause only distortions and incorrect representation of the object itself in your acquired data, but will also cause loss of resolution and blur in your images. And in fact, here we have on the left side a corrected image, so an image acquired with an objective that is compensating for spherical aberration, and the very same image acquired with an objective that was not corrected. Okay, so and you can clearly see the loss of resolution, the blur, the loss of contrast, and eventually the loss of information. So then we still haven't said what apochromat means. So we said what are the two main aberrations that are compensated by objectives. And now I will tell you that there are 3 different levels of compensation, or let's say corrections. So the 3 levels are here listed in this column, and they are achromat, neofluor, or apochromat, like the one that we were observing before, right? So objective that says plan achromat means that they are compensating for one single wavelength in spherical aberration, and specifically 546 nanometers. This is a very difficult piece of information to dig out, okay? And the chromatic aberration, is compensated for 2 different wavelengths, and specifically the 486 and the 656 nanometers, okay? So there is not even overlap between the compensation of the wavelengths done for spherical aberration and chromatic aberration. In fact, because of this chromatic aberration compensation between, let's say, the blue range of the spectrum and the far right range of the spectrum, so when imaging, like focusing in the middle of the spectrum, let's say, like where the green light is focused, we have in bright field with this objective a magenta halo. Then neofluor lenses are historically compensated for 2 wavelengths for spherical aberration. This 3 is in brackets being parentheses because they say 2 nearly 3. Nobody knows what nearly 3 means, okay? And 2 wavelengths for chromatic aberration. And achromat lenses are the most highly corrected lenses that compensate for 5 wavelengths in spherical aberration and 4 wavelengths in chromatic aberration. So now it's clear that so apochromat lenses are most highly corrected for spherical and chromatic aberrations, but it's not necessarily true that you will always need an apochromat lens. Okay, there are characteristics of neofluor lenses that so the best apochromat lenses in certain circumstances. For example, if you're doing experiments in the wavelengths that they are corrected for, or in monochromatic experiments, and you are looking, so you want to do deep tissue imaging, because notoriously neofluor lenses, they have a longer working distance than apochromat lenses have. And there are still other characteristics, okay? So in general, there is much more than this. And again, this is an invitation to talk to your local expert or refer to the community that is available within the COLife project and also the university, the Faculty of Science. So to discuss your project and to seek for support. Then, after the objective correction, so you see, we already said many things and we still didn't reach the magnification. So then we go to the magnification. Magnification, I guess everybody knows, this 20x means that this specific objective, so magnify the object in focus 20 times. So I will not say more than this. And then after the 20x, we have slash and numbered, which is 0.8 in this case. And this is the numerical aperture or aperture of the objective. The numerical aperture, it's a measurement of the maximum cone of light that can be accepted by a lens. So lenses, they acquire a certain cone of light, and this cone of light can be smaller or larger. Larger is the cone of light, more photons will be collected by the lens. More photons means so higher sensitivity of the lens, and also higher level of information. Okay, so mathematically, the numerical aperture that you see here is described as n sine of alpha, where n is the refractive index of the medium through which the lens looks. So this could be air, but could be water, oil, glycerol, and silicon, and other things. So there are many specialized lenses, okay? So, but the refractive index, what is the refractive index? The refractive index is a measurement of the speed of light in that specific medium, and it's specifically a fraction that is given by the speed of light in vacuum divided by the speed of light in that medium, okay? So for air, it's approximated to 1, because the speed of light in air is approximately the same speed that light has in vacuum. And then it becomes larger and larger with the growing of the thickness of the medium. Okay, so water has a refractive index of 1.33, oil of 1.515, and so on. Okay, so n is the refractive index of the medium, and the sine of alpha is the sine of this angle, which is the angle between the optical axis of the objective lens, so between the objective lens and your specimen, and the most inclined ray of light that it can be collected by the lens. All right, so now that we know how this cone of light is defined, please keep it in mind, because the numerical aperture is a concept that is extremely important, and we will use it later on to calculate define and calculate the resolution of a lens. Okay, so after the numerical aperture, there is another important piece of information, which is this so known or missing information, which is not actually missing after the numerical aperture. So you have to know that when after the numerical aperture there is nothing specified here, it means that the lens that you are considering is a lens that works through air. So it's a dry lens, because here, so the manufacturers, objective manufacturers specify the immersion medium for that lens. So if this was a water lens, you would have found here W for water, or oil for oil, or immersion correction for a multi-immersion lens that can work with multiple immersion medium, from water to silicon, from silicon to glycerol, and from glycerol to oil. Okay, so pay attention. This is information is extremely important, because it's extremely important to match the refractive index between the immersion medium of the lens and the mounting medium of the sample. But this is another story. We don't have the time to consider it. Again, please talk to your local expert. Then if we go further, we see this infinite sign here. So this means that the light collected from the focal plane of this objective will be actually sent parallel, so will focus to infinite, so we will send parallel after the objective. Okay, so this stays for ICS optics, which I hope I will remember correctly. It is infinity color corrected optical system. So, or as the Peter Evanet teaches, so this is like an infinity corrected lens. So projects the light parallel. This is not extremely important for you, but it is important in the case you are approaching or you are considering the idea of building up your optical system, or doing optical technology development, for example. This is not the only possibility that you have for a lens, but there are lenses that are that have not infinity tube lens, but they are finite tube lenses. And then instead of infinite, you will have here a number. The most common number is 160, which is 160 millimeters. It means that the lens in consideration will focus the light 16 centimeters after the lens itself, or 25, so 25 centimeters. These are the two most common numbers. And then the last piece of information, but not the least important, 0.17. So this one, so this number there is specified because it's extremely important and refers to the cover slip thickness. So you have to know, and you should consider, if you don't do so, if you haven't done so so far, so from this moment on, you should consider the cover slip that you use to mount your sample as part, or let's say the last element of your objective lens, because these highly corrected objective lenses are engineered to face a cover slip that is exactly 0.17 millimeters thick, okay? Not less, not more. And because the thickness of the cover slip has a huge impact on the spherical aberration that will be caused by the element itself, right? So, and in fact here in this very simple scheme is depicted how differently the rays of light are actually traveling and then refracting and diffracted by thin and thick cover slips. So then the invitation is always use cover slip number 1.5 highly selected. So just cover slip number 1.5 are not sufficient because there is a huge variability that I can tell you precisely. So the cover slip number 1.5, not highly selected, they go from a thickness of 0.16 to 0.19 millimeters. So the highly selected or high performance cover slip instead, they have a thickness guaranteed that is 0.17 plus minus 0.005 millimeters, and they make a huge difference. And I will show you here in a real picture. This is a bright field picture taken with a highly selected cover slip on the left and with a regular cover slip on the right. And look, the level, so the spherical aberration consequences that are immediately visible here. So lots of contrast, lots of resolution. Imagine if you have few fluorophores and then all the signal is blurred and lost in an elongated NZ image. Okay, so last but not least point to take in consideration, the spherical aberration is also influenced by the conditions of your lens. So these two pictures were taken by Sebastian Gliem, who is a Zeiss microscopist that works as embedded specialist in Harvard, in the Harvard campus. So this picture was taken with a clean oil objective, and this picture was taken with this very same objective, but was dirty with old oil. And what do you see here? So I bet that many of you are familiar with this kind of not very sharp signal that is very often mistaken with a incorrect sample preparation. So for example, incorrect washing or unspecific binding of your fluorophores, of your antibodies and fluorophores. And instead, it's simply the fruit of not cleaning correctly the lens. Okay. Now, I prepared a teaser slide, so let me check the time. So I'm very late. The teaser is that are these three lenses equal? So you don't need to answer to this question, don't worry. If not, why? Which one should I use for my experiment? So please talk to us. If you have doubts or you want to learn more, talk to your local expert. Let me go on because it's a little bit late. So this is just to give you the complete lens nomenclature we will not go through, and the color coding. So this nomenclature and color coding is standardized at the international level. This is you have the reference here, so you can find it on the Zeiss webpage. And please read it and ask again to your local experts. And now let's go to optical resolution. Okay, so the definition of resolution is it's not immediately clear for everybody, because often resolution is actually linked to the concept of pixel size or amount of pixels that a person has in an image. And instead, the resolution is the minimum distance at which two objects, two a-dimensional objects, for example, two source points of light, can still be resolved. And below that minimum distance, we will see those two objects as a single object, okay? So we will not resolve them anymore. So we call this minimum distance D, small d, not capital D, because it's the minimum distance, okay? And it was, so the resolution of a lens was mathematically described for the first time in 1873 by Ernst Abbe, and who found that the optical resolution, so the minimum distance resolvable by a lens, is directly proportional to the wavelength of the light that is observed, divided by 2 times the numerical aperture. Do you remember the numerical aperture, that cone of light that I told you? Bigger is the cone of light, more photons, so more sensitivity, but also more information. And in fact, bigger is the numerical aperture, smaller is D. And we want to have a small d because smaller is the minimal resolvable distance, higher is the level of details that we can retrieve from our images. Okay. But then what about the magnification? Did Abbe forget about the magnification? So no, he did not. So, I mean, the magnification factor does not determine the optical resolution of a lens, okay? So there is often the tendency to think that bigger lenses are better than smaller or less magnifying lenses, but this is not necessarily true. There are many considerations that must be done. Please, again, talk to your local expert, because often, so this is not like a rare case, there are small lenses that outperform highly magnifying lenses. Okay. But why there is a limit of resolution? The limit of resolution exists because the image of a point is not a point. This is very important, so please keep it in mind. So the image of a point is actually like a disk of light surrounded by a diffraction pattern that can be described as a concentric set of circles that are alternate darkness and light, okay? So an alternate set of dark and light circles. So the central disk of light is called Airy disk, and the entire diffraction pattern, the complete thing, is called point spread function. So which is nothing else than the way how the light spreads from a point source. Okay, so yes, an eight-dimensional point source of light. This one is actually a real point spread function that I took in one of our microscopes. And you can see here the central airy disk and the diffraction pattern. I will just zoom in, you see. And here, drawing a line profile, so a line, and calculating the line profile, intensity profile along this line. Here you have intensity versus distance in microns. You will see that we have like a progressively higher and higher signal until we reach the central disk of light that has this approximately Gaussian signal. And then again, the signal goes lower and lower in these side slopes. Then, how to empirically measure the lateral dimension of a point spread function. This is very important because it is standardized, and it's important to understand what is your resolution. I will tell you in a minute, or to verify that your system actually respects the theoretical resolution that you can calculate with the Abbe formula. So this scheme was made by Leica, and here you have like your point spread function and a line profile as I did, and this is the signal that is collected by this line profile. So in the Gaussian central signal that corresponds to what is measured by in the central disk of light. So here, this Gaussian signal, we calculate the full width at f maximum. What does it mean? So we calculate the height of this signal divided by 2. So in this way, we find the f maximum. And here we measure the distance that the full width of the Gaussian signal has. So the distance from this point to this point. This is the standardized method that is internationally recognized and respected for calculating the lateral size of a point spread function, okay? Is it constant? Can it be calculated? Yes. So the answer is Abbe. Just so that the full width at f maximum of a point spread function corresponds, or it should correspond, to the value that is theoretically predicted by the formula that Abbe described in 1873. Okay, so then this is like a visual explanation of why we have the loss of resolution, since we see this huge airy disks then surrounded by these concentric patterns of darkness and light, closer to objects are, so the least we will manage to discriminate between one and the other one. Okay, so this is a very simple explanation. This is like a theoretical, so a virtual case, let's say. This is a practical case. So I took this image with a 63x 1.4 lens, so highly resolving lens. And while we managed to resolve certain portion of this image, so these are like all source point source of lights, so 8-dimensional point source of lights. When they are too close, it's impossible for us to tell apart whether here there are 2, 3, 4, multiple. So we cannot count the sources of lights, and simply because the diffraction patterns are overlapping too much, right? So then I would like to make some consideration about the Abbe equation. So, and then you know clearly that then since there is a direct relationship with the wavelengths and an inverse relationship with the numerical aperture, smaller is the wavelength, Smaller will be this minimal resolvable distance, so higher resolving power. Bigger is the numerical aperture, higher resolving power, so smaller t. But what you might not have considered so far is that when you image a sample, you don't look at your sample. So first of all, remember that the image of a point is not a point, but it's like a diffraction pattern. But also, it means here, the further consideration is that if you have a specific structure in your biological sample that is labeled with a certain fluorophores, will have a certain image and diffraction pattern, but if you label the very same biological structure with another fluorophore that will have a different, will produce photons with different wavelengths. So you will see a different image because it will create a different airy disk and diffraction pattern, although the structure of the sample will be the same. Conversely, if you have like the same structure labeled with the same fluorophores, but you observe it with different objectives, with different numerical aperture, or different objectives with the same numerical aperture, but you have to know that two equal objectives do not exist, you will still produce different images. So please be aware that what you see through your microscope is not your object, but it's an image of your object, which is the product of like the object, all the aberrations that are already embedded in the sample preparation, staining, and so on, and then all the modifications that are given by your optical system. All right, so again, this is a further invitation to talk to your experts. So then, this diffraction pattern has also a 3D structure, it's not only in 2D. And here we see a projection in XZ. So where we have the object in the central portion of the image and the diffraction pattern above and below. So this is actually a real example that I acquired with one of our microscopes. So we see here the diffraction pattern that progressively becomes bigger and bigger, while I'm moving away with the object from the objective, okay? And you see the projection of these rings of light. Perfect. So there is therefore also a resolution in Z for each objective, a limited resolution. This is calculated again with the full width of maximum. You already know how to do it. And I want to show you here that the resolution in Z, if you see this, so the disk in the Z direction is larger than the disk that we observe in X and Y. And in fact, every single lens, so this is valid for every lens, has a resolving power in Z that is lower than the resolving power in X and Y. And in fact, there is a different equation to calculate the limit of resolution in Z, which is this one. So the minimum resolvable distance in Z is equal to 2 times lambda times n, which is the refractive index through which the lens will look, divided by the numerical aperture of the lens to the power of 2. So two considerations. First of all, so this the resolution limit in Z is inversely proportional to the power of 2 of the numerical aperture, which means that the resolution in Z will increase so exponentially with the increase of the numerical aperture. So you will have huge increases with small increase of numerical aperture. And the second thing is that it's directly proportional to the refractive index through which the lens looks. So, which means that if you have two objectives with the same numerical aperture, so but different immersion media, the one that will look through the immersion medium with lower refractive index will actually give you higher resolution. So if you have a 1.2 numerical aperture water lens and a 1.2 oil lens, the water lens will outperform the oil lens. Again, there are many considerations about this, and talk to us. So then, now that I gave you this teaser about resolution, I will tell you about sampling principle. Let me see, I'm relatively on time. Sampling principle. So let's consider 2 points, so 2 a-dimensional sources of light in our specimen that are at a distance which is d, so our minimum resolvable distance. So we can, and actually the objective collects an information that allows us to separate, resolve these 2 objects. So we will see them as 2 separate objects, okay? So in spite of the information collected by the objective, we can actually completely kill the resolution, the optical resolution that our lens gives us if we do the incorrect digital sampling. In fact, if we choose pixel size of our image that is too large, so then the 2 objects will fall in the same pixel, and then they will be translated in the conversion from analogical signal to digital signal and the digital image. They will be converted in an image that has 1 single bright pixel. So we will see 1 single object in our digital image, and we will not be able to discriminate, so to resolve the 2 objects anymore. So we are losing resolution and information. Okay, so then some of you might be tempted to think that having a pixel size that is equal to the minimum resolvable distance might be sufficient. And this because below the minimum resolvable distance, there is no information that counts, right? So analogical information. It's true that there is no, so we cannot resolve below the minimal resolvable distance. But what will happen if we will sample with a sampling factor with a pixel size that is the same of our minimal resolvable distance? It will happen that these 2 features, these 2 points will fall into adjacent pixel sizes. And then this will result in an image of 2 adjacent bright pixels that will be seen as one elongated object, right? So we are still not resolving and we are losing information. So now, by now, you might imagine that the only way to resolve these 2 objects is actually having 1 dark pixel in between. And to do this, we need to further, we need to sample with a frequency that is greater than our resolvable distance. So now, this observation, this pragmatic explanation was actually mathematically demonstrated by Nyquist and Shannon, who formulated the Nyquist-Shannon sampling theorem, which says that to correctly represent an analog signal, whatever the signal is, in a digital signal, so in our case, in a digital image, your sampling factor or digital resolution, which is like this capital D, must be smaller or equal to your optical resolution, in this case, divided by 2, okay? So, and this is like what you need to refer to. Again, like there are many considerations must be done. I will do just one. Then again, I invite you to talk to your local expert. And the one that I want to tell you is that the optical resolution here that you from which you need to tune your digital sampling is not necessarily the theoretical resolution of your lens, but it can be the resolution that you need in order to answer to your scientific question. And that's because, of course, increasing the frequency of sampling in an image has also down factors, so has cons. So increase time of acquisition, higher photo damage, the production of bigger and bigger data, which nowadays cannot be underestimated. So if you are looking at really big structures, for example, like mammalian cells, and you are interested in counting cells, you don't need to respect 250 nanometers optical resolution of your lens, but you might go into order of microns resolution. So always consider to tune your microscopy parameters and acquisition parameters in function of your scientific needs and not in function of the maximum best possible, okay? So this is not the only consideration should be done regarding this, sampling principle. But again, this seminar and this webinar is an invitation to talk to us and confront and having a project discussion, in-depth discussion with your local expert and microscopist in the entirely Lisbon area. Our opens our door. Please come and talk to us. And with this, I would like to. This is also valid for the Excel resolution. With this, I would like to thank you, and I will be open for questions either now or at the end of the webinar. Thank you very much. I will stop now sharing the screen.
Hi, David. We have 2 questions. So Erin asked, is there a specific glass we should use for the cover slips, or the thickness is the most important detail in a cover slip choice?
The thickness
Gabi and Pedro already answered, but maybe you can.
So yeah, so for my knowledge, the thickness is what is the most important detail. So it should be glass. So there are sometimes petri dish that are made of plastic or other materials, and this will greatly affect the spherical aberrations and the quality of the images. So the thickness is the most important. Yes, please use highly selected cover slip, 0.17 plus minus 0.005. And the second question?
And the second question asked by José Silva is, how can I be sure about the right lens or microscope that I should use to measure the size of a specific cell structure, for example, the thickness of a membrane?
Okay, so yes, so this requires a project discussion and clearly so understanding what is like the scientific need and not just like writing in one line, because there might be many things. I'm sure that the project is much more complicated, but then so we can guide you through the choice of the correct microscope and the correct objective. There are many things that must be taken in consideration: the resolution power of the lens, the working distance that you want to that you need to have, and then whether or not you want to do colocalization, and what is the level of signal that you will need to have. So whether you need like a higher level of sensitivity or less level of sensitivity. So whether you are doing live cell imaging or not, and so on and so forth. Even the choice of the fluorophores of interest is extremely important, because there are certain fluorophores that will grant you higher penetration depth, or they will last longer for live cell imaging. So there are many parameters. That's why before to be trained for a specific technique or a specific microscope, is extremely important for us to give a scientific support. So that's why we do project discussions and we identify together the best way to answer to your scientific question. Okay, so come talk to us. We will be very open and discuss all the possibilities. Very often there are several strategies that might, to answer to a question, and we need to basically test them in parallel. Okay. Anything else?
May I add that to that answer?
Yes, sure.
Yeah. Hi, David. Good morning. Thanks a lot. Great talk. Really cool. Touching on very important topics. Related to the question that was just asked about resolution and being able to see things, David was just showing you the formula for resolution, and this is going to be repeated on other webinars throughout this week. But if you input the numbers there for a conventional imaging session, you will notice that your best bet is being able to resolve something on the order of 200 nanometers. And if I'm not mistaken, a membrane is in the order of 9 nanometers. So you're way beyond the limit of resolution of a microscope. Having said that, like David was saying, you can see a membrane. You just can't measure it, which was what you wanted to ask, right? You can see it, but you will not be able to measure it accurately. And that'll be addressed again once you talk about super resolution and the limits of resolution. Yeah.
In fact,
So,
understanding the question is extremely important. What do you need to do? Because then we could direct you to different techniques, for example, super resolution techniques, as Gabi was mentioning.
yeah. Now, being able to see or resolve are two different things. And if by the end of these webinars that's not clear to you, make sure we explain it again, because that's extremely important. Seeing, detecting, and resolving are different things. Thanks a lot, David.
Thank you, Gabi.
Thank you. Are there any other questions? If you want to speak up, you can also raise the hand. If not, we will pass to our second speaker, Telmo Pereira, who is the head of bioimaging facility at CEDOC Nova Medical School. And he will tell you about introduction to fluorescent microscopy and light detectors.
So, good morning, everyone. So I'll just share my screen. Okay. Okay. So in the next couple of minutes, I will want to show you how so the principles of fluorescent microscopy, and so how it works. I will also want to show you how to choose your fluorophores and why you should choose one instead of others, and also just to give you an idea on how to on the main cameras and detectors that you can use in microscopy, and each advantage and disadvantages of each, so you can make better choices while you are acquiring your images. Okay, so starting at the beginning. So at conventional microscopy. So with conventional microscopy or transmitted light microscopy, which is a label-free technique, you can observe already many things. So for example, in this case, you can see HeLa cells, so a time lapse, you can see cells dividing, the cells moving, you can count the cells, you can see them growing. So you can do this without any problem. And if your aim is just to quantify mitosis or to count the number of cells, you don't have any problem. Although if you want to follow cell trafficking, or if you want to see actin dynamics in these cells, then you reach a limit of this technique. And for that, you need another technique. And in this case, you would need fluorescent microscopy. So the first question would be, why do you use fluorescence? So fluorescence is very popular nowadays, and it's a daily use technique. And the first advantage that you have, you can clearly see in the images that you already took, and also specifically in this image here, you can see that it has a high contrast. So usually you get almost dark background in very high signal. So the signal to noise ratio usually is very high, and you can see clearly the structures that you want to see, and the background is very, very faint. So in this case, you can see these microtubules very well in this image, and also the DNA, so the histone marked here in red. So another advantage is that you can also see in this image is that it's highly specific. So when you make a fusion protein with a fluorescent probe, or you do some antibody staining, you can see that you can see specifically your structure. You can observe exactly different places in the cell, different compartments, etc. So you can target whatever you want at this moment in your specific sample. Also, the fluorescent microscopy is quantitative. So you can calibrate your system and you can calibrate your system and see exactly if there are regions of your image that have higher intensity, for example, here, the centromeres, that are more intense than the rest of the microtubule zones. So you can see that you have more signal, more molecules in a specific place than in others. Last but not least, all this is compatible with live imaging. So you can, it allows you to see the dynamics, it allows you to see proteins of interest, it allows you to see many things by just recording a time lapse and seeing the behavior of your system. So this picture that I was showing you, it's not just a picture, it's a time lapse. So you can clearly see all the signals, all the cells dividing, the DNA splitting up. So everything, you can see all these advantages of fluorescent microscopy in just one image. Okay, so what exactly is fluorescence? So there are lots of definitions. They are very similar. I just picked one, and that's the one I will show you and explain you a bit further. So fluorescence is a molecular phenomenon in which a substance radiates light energy almost instantaneously upon being struck with the light from another source. So this means that you need a substance or molecule that will emit some light, and you need some light source to make that phenomenon happen. So let's find an example and see how this works exactly. So simulating one of the first observations of fluorescence by Sir John Herschel in the year of 1845, I will show you what happens when you use a UV light source and you illuminate the quinine molecule. So the quinine molecule, you must know it by heart. It's contained in tonic water. And I don't know if you ever done a similar experiment, but if you illuminate the quinine liquid, which you can see here, with a UV light or something around the same wavelengths, if you illuminate it, you will see a very bright and blue light. So one thing that you can see in this movie already, sorry. Try to play it again. One thing that you can see is that this light here has a different color than the light that is being emitted by the fluorophore, which in this case is the quinine molecule. So to explore this a bit further and to take this example into a bit more pragmatic way, so if we take the quinine molecule and we excite it with UV light, and this light would be around this part of the spectra, so around 400 and something nanometers, and you are exciting the quinine molecule. And if you compare it with the emission light, and you can already see that the color is very different, you will see that this is around 500 and something nanometers. So since this has a longer wavelength, it means that this energy, the light that is coming from your sample contains less energy. So usually in microscopy, we call the light that is absorbed by your sample we call it excitation light, and the light that is coming from your sample, we call it emission light. So one of the very important tools that we work with in fluorescence is the fluorescence spectrum. So this fluorescence spectrum is quite easy to calculate. Nowadays, you don't need to. There are lots of manufacturers that already show you what the spectrum is for each fluorophore, and for even if they found a new one, they already calculate this for you. But if you wanted to calculate it, what you could do is to illuminate your specific fluorophore. In this case, I'm showing you the quinine molecule again. So if you illuminate it with this with this light here, this wavelength, it will show you the profile of colors that will emit from your sample. So it will contain a peak, so it will be brighter around this blue part of the spectra, but you will also get smaller parts of green and a bit parts of this violet light. Okay, so if we now change the excitation light to a different zone, you can see that the spectrum remains the same shape, but now it has a different height. So you will have more intensity if you are exciting around this wavelength. So now if we go to the peak, which is on this part here, you can see you have the maximum possible light coming out of your sample. And if you do this for all the wavelengths, you will get you'll get both the excitation and the emission spectra for all your so for the fluorophore that you are interested in. So now if we look at both the peaks of excitation and emission, you can see that it's that they have a considerate difference between this one and this one. And there is a law, or it's also called Stokes shift, which is exactly this. So the difference between the excitation peak and the emission peak is called the Stokes shift. And this is due to the energy loss that occurs upon the fluorescent phenomenon. So to further understand this, I will show you these diagrams, which are called Jablonski diagrams. And this will explore how electrons and common fluorophores are excited from the ground state into the higher energy state. So this will be the ground state of the electron. This will be the excited states 1 and 2. And this will be one of your electrons in a specific fluorophore. So we are looking at the orbitals, and what happens is when a dye absorbs light, this is what it will show you here, the electron will be kicked into a higher orbital, and it will get into a higher energy state. This absorption is very fast, and it occurs in like femtoseconds time scale. Okay, so this is very, very, very fast. So once the electron is on the excited state, it will then lose a bit of energy, and this occurs through two processes. So internal conversion and vibrational relaxation. So you can see that the electron is going down in energy until it reaches the ground state of the excited state. So at this point, the electron can then go back to the ground state and emit a photon. So this would be what happens in the case of a fluorescent event. So as you can see, the amount of energy from this point to this point is different and lower than from the energy that when we started and that we went from here to around this point. So the difference between these two is lost due to this vibrational and internal conversion. And usually it's lost through heat. And this this light that will come from your sample will be of a higher wavelength, and as I told you, will contain less energy. So there are other possibilities of when the electron is in this particular state here. So one of that is the fluorescent event, as I showed you before. But there are others, and this has a certain probability of happening. I will not show you all of them. I will just show you two examples of what could happen. And in this case, this electron will not emit any light. So there is the non-radiative decay, which will, so the electron will go back to the ground state, but it will not emit a photon. So in this case, you won't get any fluorescence. And also it can happen the quenching phenomenon. So it will, the energy can be transferred to another molecule. And again, you won't emit any photon in this case. So an important definition that relates to what I'm telling you about in this moment is the quantum yield. This is a property of the fluorophore itself, and it's the ratio of the photons that are emitted in relation to the photons that were absorbed. So, for example, if you have a quantum yield of 0.5, it means that you need to absorb 2 photons in order to emit 2 photons. Oh, in order to emit 1, okay? So another 2 parameters that can be also linked with this are the brightness of the fluorophore. So the brightness of the fluorophore or the dye is determined by how well the dye absorbs the excitation light. And this is a product by this and the quantum yield. Okay, so if you multiply these 2 numbers, and I will show you later where you can find those, you will get this brightness parameter. So this could give you an idea of how bright your signal will be in your final sample. It's not 100% correct. There are a lot of things that can change the brightness of your fluorophore in your final sample, but still it's a good indication of what you can look at and to compare 2 fluorophores. If you have both on hand, you could pick the better one for your particular sample. So another one important component is lifetime. I will not talk much about this, but the lifetime is the time between the photon absorption and the return to the ground state. So the time that it takes for this whole process. So this parameter is also dye specific, and it depends also on the environment of the dye. And there's a whole form of fluorescent microscopy called fluorescence lifetime microscopy, or also known as FLIM, that you can read either you can read this time and also the fluorescence, and this will allow you to take different conclusions of your samples. Okay. So now that we know how a fluorophore works and how the fluorescence works, now we need to put this into practice into our microscope itself. So Davide already showed you a similar scheme as this. I will try to show you this again, because it's very important for you to understand how these microscopes work, because most of the microscopes you have access to have this or a similar light path. Okay, so the first thing you want and you have is the light source. So the light source can be of many types. Nowadays, LEDs are very popular, but you might have mercury or metal halide lamps in your microscope. Also, lasers, you can also have lasers. Usually they are more linked with the confocal microscopes and other different architectures, but I will show you also a bit here about this. So in the light source department, if we have, for example, a mercury lamp, you will, so this light contains multiple wavelengths. So it's a polychromatic light. So when we want to excite our sample, and you saw previously that there were differences between exciting our quinine molecule with one excitation light or another excitation light, so the wavelengths can differ. So usually you want an excitation filter to block the light that is not important to excite your sample, and also only let the light that is of interest to go through this this filter. Then you have this dichroic mirror, which will reflect the light that you want to reflect to your sample. Okay, and this light will then go through the objective and it will reach your sample. Your sample will then be excited, it will fluoresce, and it will emit a few photons of a determined amount of colors. So these colors will then be allowed to pass through this dichroic mirror. So the dichroic mirror is designed in order to reflect the light, the excitation light, but let pass the emitted light. And then usually you also want an emission filter. So to block out different parts of the emitted spectra. Sometimes you want to do this to avoid crosstalk between two or other fluorophores that you contain also in your sample. So, and then only the light that you really want will go through to the ocular or to another detector. That could be a camera or other type of detector. So this will be the main principle, the main light path of almost all the microscopes that you will see in the following days. They will have variations, of course, but this will be the main principle. So a crucial element here. So Davide already talked about the objective, so I will not touch that. I will just talk a bit about the filter cubes. So the filter cubes are these three elements here. So the emission filter, the excitation filter, and the dichroic mirror. They are assembled in this cube-like structure. They have exactly this. They have exactly this. They look like this. Okay. Also, they usually are already built into your microscope. So you already have a certain a certain filter cube for a certain fluorophore. So when you go to your microscope, you just select one specific filter, and then you can see your specific fluorophore. Of course, you can make custom filters, and that is something that if you want, it's a possibility to do so. So one final thing regarding the filter cube. So many questions arise of, is this filter correct for my sample or not? How do I read these numbers on the filter cube? So I'll just show you briefly what usually you can, the information you can get on either the software of the microscope or on the internet using the reference of the filter. So for example, this is a filter set for a Zeiss microscope. It's this one 38HE, doesn't mean anything. The information that you really need are these three parameters here. So the excitation, the beam splitter, and the emission. So usually these numbers have a number, then a slash, and then another number. What this means is this is the band of excitation center. So in this case, it's 470 nanometers. And then the next number is the bandwidth. So the bandwidth, it's how large this band of excitation is. So how do you read this? You read this that the excitation will go from the band center, and you have to subtract the bandwidth halved by 2, okay? And then you have the 450 until 490. And then you can see that you are exciting your fluorophore exactly from 450 to 490. This correlates with this plot here that you can see. Sometimes you have this information, sometimes you don't. You can read this as the so this is the percentage of transmittance of a specific signal, and you can see it's more or less from 450 until 490. There's where you get the highest band pass for the excitation, and also you can do the same for the emission. The beam splitter, usually it's in the middle between these two. So this will reflect the light from the excitation, and it will let pass all the light from the emission, okay? So this is exactly in the middle, okay? Okay, so now moving a bit into fluorophores. So now that you know what is fluorescence and how you can use a microscope to observe a specific dye, we will take a look at the fluorophores that you can use. So historically, one of the biggest events that kickstarted microscopy was the discovery of the GFP molecule, so the green fluorescent protein. So it was discovered many years ago. It was awarded a Nobel Prize in 2008. Nowadays, there are lots of proteins, so fluorescent proteins that are derived from the GFP and others. At this point, you have multiple colors. They go throughout all the visible spectrum. Some are better than others. Some have more brightness than others. Some have more quantum yields than others. But they are all important and all very useful. So also, not only fluorescent proteins are available, but there are also lots of dyes and kits and other types of fluorophores that you can use to illuminate your cell, as you are seeing here in this scheme. So nowadays, almost every component of the cell, every protein has some type of fluorophore or fusion protein or other dyes that you can use to illuminate specifically and with high contrast your target protein or your target organ. So each fluorophore has a characteristic excitation and emission spectra. So you can see, so I'm showing you here these 4 examples. So GFP, Alexa Fluor 546, M Cherry, and Alexa 647. You can see that they are all very different. The shapes of the excitation are a bit different in others. There's some are shifted more towards the green part of the spectrum, some more towards the right part, and the infrared part of the spectra. And what is important is that they are very characteristic, and you can in fact simulate how those how these fluorophores will behave when they are together in a specific configuration, so in a specific cell, in a specific sample. Okay. So one of the most important resources you can use in this regard is a spectral viewer. So you can search in Google for spectral viewer. There will appear a very, very big list. Usually the first one is from Thermo Fisher, but there are from Chroma and from others as well. They all work usually more or less the same way. So you have the excitation and emission profile for almost all the dyes. And what is very interesting is that you can simulate your samples and choose the appropriate dyes in order to have the best separation you can in terms of spectra between the fluorophores that you want. So in this case specifically, we have these 2 fluorophores. They are very close to each other. And if we use this light to excite it, you will see that we are both exciting this green dye and also this yellowish dye. So if we don't get only this yellow, so this rectangle, this from the, so if we don't select only this band of emission, we will get crosstalk between these 2. So it's very important in this case to choose an appropriate filter or to configure a microscope to reject all the light that goes from this part in order to get a pure signal of this fluorophore. So this is very important, and this is one of the things that you should pay attention and do before you prepare your sample. So even before you prepare your experiment, you could already do this and already buy the fluorophores, the more appropriate fluorophores for your particular experiment. So another important resource are fluorophore databases. So I will show you, I'm showing you here 2. This one, this FP base, is very good for fluorescent proteins. And this one here down contains also information for fluorescent dyes. And what the type of information you can see here, besides the fluorescent spectra and many more things, are 3 things that I already talked about. So the quantum yield of this protein. So this is the enhanced GFP, okay? So you can see already the brightness of it, and also you can see the lifetime of it. So you can do, you can study which will be the best fluorophore for your particular experiment, which one will be the brightest one, and also combine this with the fluorescent spectra and see if they are separated enough or not in order to get the best out of your image. Okay, so now moving on to the last part of this fluorescent part of the talk, and I will end it with photo bleaching. So photo bleaching is the number one enemy of imaging. So maybe not the number one, but it's one of the top enemies of imaging, because what it happens is that once you are exciting your fluorophores over and over, there's a certain probability that they will lose the ability to emit light. So they will stop emitting light over time. This is worse when you are doing live imaging. And you can see that, for example, in this movie here, as minutes goes by, the signal goes down and down. And if the movie continues, the signal will completely disappear. So this is what we don't want. We want to follow our samples over time. We want to do our big Z-stacks, and we want to have all that information, but we don't want to lose the signal, because if the signal disappears, you get you lose everything. You can get wrong conclusions, because if you have higher signal in the beginning of your Z-stack, and then if the signal goes down and down as you go along the Z-stack, then when you are doing some calculations, you can take wrong measures. So you really need to pay attention to this. Either if you are doing a time lapse or a very big Z-stack, this is very important to pay attention to the photo bleaching effect. So this process is enhanced by the usage of high excitation light power. So if you use more laser power, more fluorescent lamp power, you will enhance this. And so you will see it almost immediately, okay? So what can you do to try to minimize the photo bleaching? So the first thing you can do is to select more stable dyes, more so dyes that will be more resistant to fading. Okay, this can also be seen in those websites that I told you about. So the second thing that you can also do is to increase the label density. So if you increase the density of your label, you have more fluorophores to work around, and then you will then decrease the amount of disappearing of your dye. Okay. So the third thing is to decrease bleaching by using anti-fade compounds. So these anti-fade compounds, usually what they do is they reduce or remove as much molecular oxygen as possible from your sample. So these compounds, you can add them to your mounting media, or usually some mounting media already contain them, and they remove this oxygen in order for your sample to be more stable and to be more resistant to bleaching. So last and not the least is to minimize the exposure time and the excitation power that you use. So if you reduce the laser intensity or the excitation light intensity, you will then reduce a lot the exposure time, the exposure to this high intensity light, and reduce then the phenomenon of photo bleaching. So now shifting gears to light detectors in microscopy. So now we already know a bit on how the fluorophores works, how the microscope works in terms of fluorescence, what the fluorescent is. Now we want to then detect this signal. So in order to, we need these light detectors because we cannot really trust our eyes. So these detectors allow us to register the images we get on the microscope. They allow us to do reliable intensity measurements, and they are much more sensitive in comparison to the human eye. So if we look at this graph here on the right, here on the bottom part, on the x-axis, you have the wavelength of radiation. And here you have the quantum efficiency of each of these detectors. So the quantum efficiency is how likely it is, in simple terms, for this this detector to detect this particular wavelength. So you can see that the human eye is just on this part here of the spectra. You can see most of the visible light, but with not a very high quantum efficiency. Okay, and if you compare this with other types of light detectors, so for example, the photomultiplier tube or these CCD cameras, you can see that it's much higher, and the response in the wavelength is also much better. So you can see more types of fluorophores, and you can see them with a higher efficiency. Okay. So globally, all detectors work in a similar way. So you will start by using your sample. So you will excite your sample as I told you before. Then this from your sample will emit photons. These photons will reach the detector. The detector will then convert the photons into electrons through the photoelectric effect. Then the charge, or the number of electrons, is converted into a voltage, and this voltage is converted into a digital number. Generally, this is done in an analog to digital converter, part of the detector, and then you get this digital number. This digital number is then sent to the computer, and the computer will show you the image. So this is what generally happens in all the detectors that I will show you in the next slides. So the most common detectors are of two types. So the first type is single point detectors. So single point detectors work so they detect just a single point of light that reaches this. So we have a beam of light illuminating your sample, and this beam of light will emit, so it will excite your sample in a particular point, and then it will, this particular point will emit a determined amount of light, and this light will then be detected by these single point detectors. So in order to create an image, what you need to do is to either move your sample. Okay, this is one of the options, but the most common is to move the beam. So if you illuminate your sample and scan it from side to side, you will then create your image. So this is the principle of confocal microscopes, for example, that José Rino will talk about in a second. Also, what happens here is the same. So the photons will reach the detector, which will then be converted into electrons, into voltage, and into a digital number. Okay. So these particular single point detectors are very, usually to create an image, it takes a long time because you need to go point by point in order to create an image. The bigger the image, the longer the time it takes to create a single image. Okay. Now, if we move then to multiple point detectors, so in this case, you use a lens to project exactly the image into a multi-point detector. So these multi-point detectors usually are an array of different detectors, and you can see in almost all at once your image, okay, depending on the magnification, of course, but everything that is on the field of view of your microscope, you will usually see it on and projected on this type of arrays. So usually this type of arrays are cameras. So now moving into a bit more detail about the single point detectors. So one of the most common ones are the photomultiplier tubes. So this work has, I'm showing you in this image here. So the first element is a photocathode, which will convert then the photon that comes through here into an electron. The electron will then be attracted to these dinodes here and will travel through them and be accelerated and multiplied depending on the voltage that you insert into the system. So if you tune in the voltage, you will get more amplification of the signal until it reaches the anode. When it reaches the anode, it will then be converted into a voltage and then into a digital number. So I can play the movie and then you will see more or less what is happening. So one photon reaches here and you can see that it multiplies many times until it reaches the anode. So you can detect faint signals because they will be multiplied many times, and when they reach the anode, they will produce enough charge in order for you to detect your particular signal. So these detectors are very linear. So they have a very high amplification of signal because of this process that I show you here. They have a very fast response. So usually, since you, for example, if you use, if you look at a confocal microscope, you can see that you need to go very fast because otherwise you take a very long amount of time to take a single image. So usually each pixel takes around 2 microseconds or something like that to take, and it's not enough time to get many photos. So usually the images are not are usually very noisy, okay, even though they are taken very fast in terms of pixel by pixel. Then you have the downside of these are the low quantum efficiency. So usually you only have around 25%. So this can translate to, on average, you need to hit with 4 photons in order for 1 photon to go through this whole cascade and to reach the anode. So nowadays, these photomultiplier tubes are using a new technology. So they basically, they replace this photocathode using this gallium arsenide phosphide photocathodes, also called by GASPs. And this has improved the efficiency to around 45%. So another type of single point detectors are these avalanche photodiodes, so the APDs. So this is based on a semiconductor material, and it's very similar to a CCD sensor used in cameras. So what happens here is that the semiconductor material absorbs photons in this area, and then you create a very high voltage in this region here. So what happens is that when the photons reach this part of the detector, they are amplified and they are accelerated here. And then by a phenomenon which is called impact ionization, they elicit extra electrons out of the material, as you can see here depicted in red and blue. And it amplifies the signal, which then amplifies the charge. The charge will be read and then converted into a digital number. So these detectors have a much higher quantum efficiency, but the downside is that they overheat if they run too fast. So they are slower in acquisition when you compare them to the traditional PMTs. Okay. So one of the types of detectors that you probably have in your institutes is the hybrid detectors. That's a property of Leica. And these are a combination of these two technologies that I show you. So they are called hybrid detectors exactly because of that. So they have GASPs, photocathodes, and vacuum tubes. And so the architecture is similar to a PMT. But then they have semiconductor electronics like the APD in order to create this avalanche of electrons in order to detect your signal. So they have some advantages in terms of light detection and others that I won't go into any details. So now in going into the camera part, I'll try to speed up a bit because I'm a bit late. So cameras usually look like these objects here on the right. They have usually they are very big for the central element that is the sensor, which is only this part here. Usually the rest is electronics and cooling that you really need in order for the cameras to work. But the heart of the camera is only this part here, which is the sensor, which will detect exactly your signal. So using cameras, so the multi-point detectors, you can create your 2D image at the same time. So you will see everything at the same time. You are not going pixel by pixel. So this makes them much faster than PMTs. Also, they have a very high quantum efficiency. Depending on the technology, it goes up to 99%. You can acquire RGB images using this technology if you want. And there are quite a few types available and variations: CCDs, EMCCDs, CMOS, and SCMOS. So traditionally, so they are, so the heart, as I already told you, is the sensor. The sensor is just an array of rows and columns of different elements. Usually each element is similar to an APD detector. So it contains the same photosensitive material. So it consists of a silicon semiconductive material. Then photons are coming into this part here, and then they accumulate in this potential well. So these particular detectors are produced in similar ways on how our chips in our computers are produced, so our processors, etc. Photons that hit these are converted into a charge in this potential well, and then they are read by transform into voltage and read into our computer. So there are two main architectures for cameras. So one is this complementary metal oxide semiconductor CMOS. And in this case, each pixel of your camera has an integrated amplifier and integrated logics in this particular pixel. As you can see, so if all this is a pixel, only this part here is the sensitive part. So this is all where the light will be detected. So you are in this particular architecture, you are throwing away a bit of light that reaches your camera, because only this part will detect it. Usually you have some lens and some things that try to converge all the light into the photodiode, but you are wasting a bit of light. So these cameras then transfers voltage into the analog to digital converter. They usually are very fast. They have a bit of noise, and as I already told you, the detection area is a bit reduced because they all contain all of these electronics in each pixel. On another technology, so the charge coupled devices, or CCDs, they only have one readout amplifier. So the signal is only read once. So you don't read each pixel, you read only after all pixels have acquired some potential. So they transfer the charge and not the voltage. They usually are slow because the information needs to go through a series of events that I will try to show you very fast. They are very precise, and in this particular architecture, if you use binning, it will amplify the signal, but it will not amplify the red dot noise. So usually it's a good strategy if you want to amplify your signal to use binning on these devices. Okay, so I will not talk about this because I'm running out of time, sorry. And now I'm just moving on to the newer technologies that or the more advanced types of cameras that usually are the ones that are being used nowadays in microscopes. So one is the SCMOS, that are the scientific version of the CMOS. Usually now they are very, very, very fast. They have big sensors with low pixels, so you can get very high resolutions with these cameras. The quantum efficiency nowadays is very, very high, and you will see more and more these cameras appear in your institutes very, very briefly. The EMCCDs, it's already quite old in terms of microscopy technology, but they are still being used because they are very, very efficient. The quantum efficiency is 99%. They have very low read noise. They amplify the signal inside each pixel, and usually this amplification is very efficient, and you can detect single photons without any problem. It allows for fast imaging. The downside is that usually they have lower resolution sensors that limit the resolution of the whole system. So my final slide here is just a small small thing, is that all these cameras are black and white, but usually you will see that in some microscopes you might have color cameras. So these color cameras are not different in terms of technology from the others. What they have is that they have filters on top of the pixels. So for example, here, this will be 4 individual pixels, but then if you put on top of them these filters that will detect green light, red light, and blue light, you can then discriminate and see if this pixel is more red or more green or more blue than the others that are next to it. So usually you have this type of pattern, this Bayer filter pattern, and you can create images in color if you want. But for fluorescence, usually you don't want to use color cameras because this architecture reduces a lot of light. So if you have the option to use a black and white camera for fluorescence, you should do so. If not, then you need to pay attention that you are losing some light when you are using this type of cameras. Okay, thank you. And now I don't know if I have time for questions, but I will I will let the moderators decide.
Hi, Telmo. Thank you very much. Before we move into Rino, we do have one question from Aaron, which is a very good question. So Aaron asks, let me guess, if we are unsure what camera we should use for our biological question, technique, Davide will tell us to contact our local facility head. I write this because I assume there is no rule we can use in camera selection. Is it correct? To select properly, we need to know a lot, which is why we have the microscopy community to help us. Exactly. Would you like to comment on that, Tom?
Okay, so let me stop. Maybe this. So yeah, you of course you need to discuss with us what type of camera you want to see, or what different architecture you want. Usually the microscopes, so when they are bought, they already contain like the best camera possible for that particular system, for that particular point in time where it was bought. So usually you are already well served on that regard. But this is also to so my idea to show you this was to give you an idea that there are multiple techniques that you can use, and these techniques that you should be aware of, that using binning, for example, on a CCD camera and or a CMOS camera is a different thing, and it's not, you should not take the knowledge of one system and just take it directly to another without knowing a bit of how the system works. So you need to know a bit about it, even if you don't know everything. And if you have any doubts, you should talk with us, and yeah.
Thank you, Telmo. So we have one more question, but before I get into that question, we'll have now a 5-minute break. So we'll have Rino's talk at 5 past. So if you want to go grab a coffee or something like that, feel free to do so. But if you're still keen on listening to Telmo a bit more, let me ask Telmo another question. So we have a question by Dinesh. What should be the minimum Stokes shift value for IHC double staining with GFP and Alexa Fluor 555? Very specific.
But maybe let me read this.
It's in the chat. So who is not interested in this question, feel free to take a break.
So the question is for double staining with GFP and Alexa Fluor 555. When you talk about Stokes shift, we talk about the difference in excitation and emission peak for each single fluorophore, so not for two different fluorophores. Okay, so GFP will have its Stokes shift, Alexa Fluor 555 will have its own Stokes shift. So the question is particularly which filter sets could we use to image both of these dyes, which are actually very similar. So GFP and Alexa Fluor 555 with a typical green filter set will basically look the same. So this might be a tricky one. I mean, we might go for specific bandpass filters with very narrow excitation and emission to separate both dyes, or we could go with spectral imaging, which we can also do at COLife. We could acquire the emission spectrum of these fluorophores in the confocal prepared for spectral image and do spectral unmixing. So there are a couple of options here. My reply would be, don't use these stainings. don't go for two green dyes. Choose a green and a red dye. Try to have them spectrally separated so that you avoid trying to go with very specific narrow filters that will cut down your photons a lot. So unless you really have to use this and we have to go into spectral mixing and things like this, my advice would go just to pick fluorophores that are really spectrally separated, green, red, far red.
I would like to add something, if possible, to this. So I would like to point out a tool, a very important tool for this, to plan in advance your experiment, your imaging experiment, guys. And this tool is the Thermo Fisher Scientific Fluorescence Spectra Viewer. I will share my screen for this, so I will give the possibility to the audience to see what I'm talking about. So, and it's here. So can you guys confirm me that you see the screen? Okay, yes. So this is the fluorescence spectra viewer. So you can type here your fluorophores. So let's see GFP. So we usually use enhanced GFP.
Sorry, I just realized I made a mistake. I thought it was Alexa 48. Alexa 555 is actually a red dye, so that would be great too. Yeah.
So I don't understand why it doesn't give me. So. And then, so you type your fluorophore and you have like a dashed line, the excitation curve, with a solid line, the emission curve. And then you want to add another fluorophore. And then here is your, for example, it was Alexa Fluor 555, right? So I think that if we type 555, we will find it exactly.
Yeah, I was going for the worst case scenario, Alexa 488.
Exactly. So the GFP and the 555, they have like this distance in peaks between the emissions. So we have a peak of 520 nanometers and a peak of 575 nanometers approximately. So then here you see also where the tail of emission propagates, so until when, and the tail of excitation of the next fluorophore, where it is, and how they overlap. And if there is like an initial portion of emission of the fluorophore, the second fluorophore, so that is overlapping with the emission of the first fluorophores that you have. So you can even add light source and excitation filters, and you can see which one is the excitation filter that will actually give you the secure band of absorption that will not allow through like, let's say, crosstalk or like a contribution of the red signal into your green channel. So from this graph, you see that if you acquire, so if you excite with your 488 light source, for example, a laser, you should absorb having these two dyes, so the peak of the GFP, but not farther than 530 nanometers that you can see here in this bottom corner here, where like the coordinate in nanometers of the spectrum, because here you already have like a small tail of emission of the 555 that will be co-excited for 488 nanometers by your argon laser. So in fact, if I add a laser and I say that my wavelength of laser is 488, let me see if it works. Display. The V custom green. No, sorry, blue. 488, excellent. So here the plot even tells you how much is the percentage of emission of the 555 that you will have while exciting the GFP with your 488 laser. It's a very interesting and flexible tool that everybody should know and use to plan in advance his own experiment, together with the knowledge of what you have available in your facility or in your own microscope in your lab. With the filters that are available, if the filter that you have available is a filter that goes from 500 nanometers to 600 nanometers. So it's a broad band of absorption for monochromatic GFP experiments. It's useless to plan to stain your sample with these two fluorophores, and then it will be better to use a further red-shifted dye. But if you have the possibility to choose, or if you have the possibility to tune your absorption, so the portion of the spectrum that you will absorb and detect, then you know that with this setup, so you should absorb the light until 530 nanometers approximately, and no further, to avoid the possibility to collect in your green signal the part of the red signal. That's it. So, and there are more and more tools and more possibilities, and you can complicate here the whole scenario. So please take a note, Thermo Fisher Scientific fluorescence spectral viewer. Very easy to find, just Google it. I will stop sharing now.
Thank you, Davide. So that was a perfect way to fill our break with a lot of information.
Yeah.
And now,
maybe Dinesh just raised the hand. Maybe we didn't answer completely to the initial question. And I'm sorry, I'm confused about the fluorophore. Dinesh, do you want you raise your hand? Do you have an additional question, or maybe to clarify your initial question?
Hello.
Hello.
Am I audible? Hello.
yeah.
Yeah. Hi, Telmor, and hi, all of you. It was a nice presentation. And may I ask one? The purpose was to ask the stock shift. So while doing the IFC triple colors, what is the best choice? Like you have the GFP and Sci5, and in between, what will be the one that we can choose? Will you please suggest something on this? If I want to detect the three proteins in same slide, so that I can see it's in the nucleus or in the cytoplasm, or are they together? So I want to do triple staining. So for that purpose, what will be the what are the filters that I can fluorophore that I can choose, and what is the validated method of quantification that I can apply? Like I tried with the area fraction, and but while doing area fraction, I had some artifacts while and it didn't give me the result. So will you please suggest something with the quantification also? Thank you.
Dinesh, on due to time constraints, we'll give a very short answer. So the short answer is that there's not an answer for your question. So you have to consider several factors when you're considering something like that. So it's not just the spectral separation when you're doing a staining. You have to consider if you're using fluorescent proteins and organic dyes, because the intensity of your different probes will influence how well you see your signal, and your signal above background will also influence how well you can colocalize things in different parts of the cell. Okay, so there's not really this fluorophore, and a third fluorophore answer to that question. So I think this is very important to tell you because you were asking this, but what you can do is write that question on the chat, and we are basically creating a Google Doc with all the questions that were asked, and then we will send the answers to the attendees. Okay, so write as much of a detailed question as you want, and we'll try to address it. So now this said, let me introduce Jose, which is Rino, which is the facility head at IMM, and with great knowledge of microscopy all throughout. And we're looking forward to hearing his talk.
Thank you, Pedro. Thanks a lot for the kind introduction. So let me share my screen. Is it working? Oh, sorry. Share screen.
It's working.
It's working? Okay.
It's okay.
All right. Let's go for the final lecture of today. Good morning, everybody, or good afternoon, maybe. So I'm going to talk to you about confocal microscopy and optical sectioning and how we can use it to acquire 3D images of your samples. Okay, so of course, to acquire a 3D image of the sample, what we need to do is to acquire a series of images of slices through your sample. So ideally, you take an image of the focal plane, of a single focal plane, and by moving the objective up and down, you can acquire a stack of optical sections of slices through the sample. We call this a Z-stack. So here's just an example. Sorry, let me just minimize this. So here's an example of a Z-stack acquire of a myofiber. This is from William Broman at the IMM. It's a Desmin staining. So we have acquired a Z-stack throughout the sample. And by stacking all of these together in a computer, we can reconstruct it. We can see how it looked like viewed from different angles, and therefore get an idea of how this structure, how this myofiber looks in 3D. So I'm going to tell you how we can do this and how we can use confocal microscopes and other optical sectioning methods to do 3D imaging. So, sorry, let me just close this. Okay, so Telmo has shown you the optical path of a wide field microscope, of an epifluorescence microscope. And of course, on a wide field microscope, we use direct mirror objectives and tube lens to form an image of your sample here on the camera. And the illumination on a wide field microscope, as the name says, so the illumination is performed over the entire sample. Okay, the whole field of view is illuminated, and here this box represents our sample. And if we have a single fluorophore on the focal plane that will emit light in all directions, part of this light will be captured by the objective, focused by the tube lens on the camera, which is placed at the image plane, and so a very focused image of this single fluorophore will be imaged by the camera. Now, the problem with wide field microscopes is that we cannot really do optical sectioning with it because, as you can see, since the whole sample is illuminated from top to bottom, if you have also fluorescent molecules in planes above the focal plane of the sample, the image of these fluorophores will not be formed in the image plane of the camera, would be formed a little bit above. So you would have a disk of autofocus light being imaged in the camera. Same thing applies if you have fluorophores beneath the focal plane. So these fluorophores will also emit light, which will be focused short of the image plane and then getting out of focus again. So you'd image an autofocus disk of light. So in a wide field system, if your sample is thick and if you have fluorophores, if your sample is fluorescently stained and kind of thick, you'll be basically exciting all the fluorophores along the Z of the sample. All of them will be emitting light, which will be imaged by the camera, and so you will have not just an image of the focal plane of the focused part of the sample, but this will be confounded. You'll have autofocus fluorescent from planes above and below the focal plane, which will add blur and basically decrease your signal to noise ratio on a wide field microscope. And this gets more problematic the thicker your sample is. Okay, if you have a thin sample, you can get a focused image if you use a low NA objective. But as your sample gets thicker and thicker, it might even be impossible to resolve anything on the sample. So particularly if you're trying to image a brain, for instance, with fluorescently labeled neurons. As you can imagine, there are many of them. The brain is very, very thick. So this might be a problem. You might not even be able to image anything fluorescent on the brain. And this was something that, many people thought about during the years. One of them was Marvin Minsky, a name that you might associate with artificial intelligence, robotics. he was a brilliant scientist. He's credited as being the inventor of the confocal microscope. He certainly filed a patent for it in 1957 that you can see here. And the idea that occurred to him was, you know, the way to eliminate all of this autofocus light was never to allow it to reach the detector in the first place. So you can see from his patent application here, his very clever idea was to use two small openings, the famous pinholes, one for illumination, another one for detection, so that light coming from the lamp would just be focused on a tiny spot on the sample, on the focal point of the objective, and the light emitted from this fluorescent point emitter would be collected by another lens and focused on a pinhole. So these pinholes will be placed in conjugate focal planes, meaning that if it's in focus in the focal plane of the objective of the objective here, it would also be focused in here on the plane of the pinhole for detection and for the illumination. And that's where the name confocal comes from the conjugate focal planes, confocal. So that's his idea, just to illuminate one spot in the sample, the focal point, and to capture light only from that focal point. Of course, you know, Minsky is credited to invented the confocal microscope, but the same idea actually occurred to different people in different places. This was later developed also by Egger and Davidoff at Yale, by Shepard and Gleason in Oxford, and by Fred Brackenhoff and colleagues in Amsterdam. So the confocal has really many different fathers in different times and places. They kind of came up to the same idea, but Minsky filed a patent for it, so he's the inventor. So how does the confocal microscope that we use nowadays work? So we basically, we don't use a pinhole for illumination. Instead, we use a very intense laser light source. We need a lot of photons for this. We use a collimating lens to expand the laser to fill the back aperture of the objective so that light will be focused on the smallest point possible in the focal plane. So by expanding the laser light and filling the back focal plane of the objective, we achieve this. So we are just illuminating one small point in the focal plane of the sample. Light is focused there. We are still illuminating above and below, but most of the photons are being focused in this point. Now, because we are still illuminating above and below the focal plane, we still need to remove this autofocus light. And for this, the pinhole is being used at the conjugate image plane to the focal plane. So a pinhole is placed here in front of the detector that will reject autofocus light. How so? Well, if we have a fluorophore placed above the focal plane of the objective, we saw that before, so it will not be focused at the image plane, but a little bit above. But now there's a pinhole here that physically rejects most of the light coming from this plane, from this imaging plane. So it will basically be obstructed by the pinhole. Only a tiny fraction goes through. So we are rejecting most of the light coming from planes above the focal plane. The same thing from planes coming below from light coming from planes below the focal plane of the sample. These would be again focused here. Then the autofocus disk of light would basically hit the pinhole, and only a small fraction would go through. So by placing a pinhole here, we are basically just capturing light that comes from the focal plane from a single point, reaching a detector. Now it's of course the main feature and also disadvantage of this design. This works fantastically, but only for one point at a time. Okay, we can collect very efficiently light from this point, but in order to construct an image, we need to have many points. We need to scan the sample point by point to acquire an image. So as Telmo was mentioning in this talk before, we are going to replace the detector. It will not be a camera on the point scanning confocal microscope. It will be a photomultiplier tube. This photomultiplier tube will amplify the signal, will detect photons and generate a high and generate kilotons, highly magnified signal that we will use to determine the intensity of light that we'll place in a pixel in an image. In order to do the scanning of the sample, we had scanning mirrors that basically they change the entrance angle of illumination in the objective, therefore moving the illumination spot. So these scanning mirrors will tilt, will move in X and Y, and will be able to move the illumination spot in the sample. This occurs very, very fast. So we are illuminating one point in the sample, collecting light from that point, integrating the signal on the photomultiplier tube, which will give us an intensity value that we place on the pixel in an image. In front of the laser, we will place an acousto-optic tunable filter that it's basically a crystal that resonates at different frequencies, and depending on the frequency that it's vibrating at, it will allow more or less laser light to go through. So we can also control in very short time and with very high precision the amount of laser excitation that is hitting each point on the sample. We will not speak about this in great detail, but we can actually use confocals to control the illumination in specific regions in the sample with pixel precision, control the intensity of the laser. And this is very useful for experiments where we want to use different illumination settings for photo bleaching, for instance, for FRAP experiments or FRET. We'll not talk about this, but the point scanning confocal is perfect for that. Okay. So this is the principle of the modern-day confocal microscope, a very intense laser light that will fill the back aperture of an objective, focusing to a single point. That point will be moved in the focal plane of the sample by scanning mirrors. This is the light that is emitted by that point will be captured by a PMT after going through the pinhole to make sure that we are rejecting light coming from planes above and below the focal plane, and we will measure those photons, we will quantify them, and you'll get an intensity value that we will use to build an image on a microscope. So we have no camera, we don't take photographs, don't take pictures with the confocal microscope, we build an image on the computer pixel by pixel. So Telmo already talked to you about the photomultiplier tube. I will not go in great detail. I'll just say that it's the detector of choice for a confocal microscope because it's a very, very fast detector, as Telmo said. So it's able to, from a single photon hitting the photocathode, it's able to generate millions or tens of millions of electrons that we can quantify. So it achieves a very high gain and it responds very rapidly to a flux of light intensity. So it's ideal for, for measuring in short intervals of time the photons that come from the tiny spot on the sample. It's not very efficient at it though, as Telmo mentioned, only around 25% of the photons will generate a signal. So it's high magnification, but not very sensitive. All right. So what about the pinhole? Which size of the pinhole? What's the size of the opening? That's also something that we can control. And ideally, when you are doing confocal imaging, you tend to go for one area unit. Where does this come from? So as you remember from David's talk, the image of a point in a microscope, it's not a point. It's actually a three-dimensional pattern of light interference, which is called the point spread function. So it looks like this in XY. You see the the brighter area disk, then with rings of interference that spread. No matter how small the dot, if it's below the diffraction limited, you always see a point spread function of the same size that will depend on the wavelength of light and on the numerical aperture of the objective, if you remember from David's talk. So, we're scanning point by point, we're focusing light on a single point in a specimen. If we have a single fluorophore there, what we will have reaching the detector, reaching the pinhole, is this point spread function. And of course, the optimal size for the pinhole to get maximum, to get best signal and resolution would correspond to the size of the point spread function of the hairy disk here in XY, depicted here in XZ. So remember the formula from David's talk. So the size of the pinhole would be, the size of the point spread function of the hairy disk multiplied by the total magnification of the system. So it's the image of the point spread function that's reaching the that's reaching the photomultiplier tube, the detector. So this value here that we can calculate very precisely, it's the 1 Airy unit. Why is it so important? Because it gives us the best compromise between a resolution in X, Y, and Z and signal detected. So as you can see at 1 Airy unit, we have still a high intensity of signal, and we achieve optical sectioning. So the size of the optical slice thickness in Z is close to its minimum. We can close the pinhole further down a bit to gain increased resolution in X, Y. So we could see our point spread function a little bit smaller, but that would mean a sharp decrease in intensity if we do it. So yes, we could increase the resolution by closing the pinhole, but we lose a lot of signal. Of course, if we open the pinhole, then what we get, basically, we don't get an increase in XY resolution. What we start to have is an increase in the optical slice thickness. So we start to lose resolution in Z. If we open the pinhole completely, we totally lose the optical sectioning ability of a confocal microscope. Hence why, when you are doing confocal imaging, you aim for this 1 Airy unit opening of the pinhole. Bear in mind that this will depend, of course, on the wavelength of light that you are using. Okay, one Airy unit pinhole will be different for 88 nanometer excitation or for 633 nanometer excitation, and the fluorescence emitted by the flow force. And so. Coming back also to the objectives, the optical thickness that you get when imaging through a confocal will also be highly dependent on the objective that you are using. So these are Z-stacks, these are XZ projections of, I'm sorry, maybe let me just point to options, slice. So these are XZ projections of a 10 micrometer bead. Notice that when you are using high magnification objectives with high numerical aperture, you are able to resolve the 10 micrometer bead in Z direction. You are able to actually measure it, whereas if you're using a low magnification, low numerical aperture of objective, you basically lose the optical sectioning ability of a confocal microscope, and what you see is very similar to a wide field microscope. So using a low NA lens, low magnification, low NA lens, you basically are not able to get optical sectioning on the confocal on a confocal microscope. Well, you can do it a little bit compared to wide field, but it's not as good as a high numerical aperture objective. So this is what a confocal modern day confocal looks like. This one is already 5-6 years old. This is a Zeiss LSM 710 that we have at the IMM, just to show you how it looks like. So this is a microscope body. This one has a large cage incubator in it for live cell imaging. This is the confocal part of it. Okay, so this is the scanning head of the confocal. It's in here that you have the scanning mirrors, that you have the detectors. The lasers are more to the left. They are there's an optical fiber that guides it through the scanning head, and this is, of course, is the computer used for acquisition of images with the software that controls it. But this is the scanning head of the confocal. Okay, when you look through the eyepieces, you are still looking at the epifluorescent wide field image. It's not confocal. You'll see what you see in the normal wide field microscope. And in fact, back here under the table is the fluorescent lamp that we use for normal epifluorescence imaging when we look through the eyepieces. When we switch to confocal mode, we'll be using lasers for excitation. We'll be using the scanning mirrors and the PMT detectors on the scanning on the confocal unit, and the image will be built on the computer. This is a confocal from the 1980s, just to compare. This is a photo that I took at the University of Amsterdam of Fred Brackenhoff's confocal. So we have evolved a lot. See, this is a complete analog system. The image will be formed here on this oscilloscope. So, you know, I can't really tell if it got easier or more difficult to do confocal imaging with all the parameters that you can control. It certainly got a lot easier. So when you're using a confocal microscope and think that the software is maybe a little bit too complicated, it's actually got easier with time. Okay, this is one of the earlier confocal designs, and you have all of these controls to adjust the image that you'd see here on this oscilloscope screen. This was fully functional until a few years ago. You could still take a sample there and use it. So because you can control all of these parameters for imaging, you can, you know, everything is motorized. You can control the scan speed. You can control what's the time that the laser spends at each point in the sample. What's the image size? What's the number of points that you'll be acquiring, and in which area of the image of the field of view of the objective you'll be acquiring it? What's the laser intensity? What's the detector gain? So, you know, there's not a single set of parameters that will make it the best possible image for every possible scenario when using a confocal microscope, and that's why it's sometimes considered an art. You have to know what you want. You have to know what you are, what's the purpose of your experiment, and you really have to choose whether you want speed or resolution or sensitivity. You cannot have it all, and you have to make choices on whether you use, you know, higher laser intensities and higher detector gain. This means that you'll have more signal, but maybe you'll photo bleach it a lot, and you'll have to go slower. So forget about speed. Possibly you have to reduce the number of pixels, so you also not have resolution. So depending on what you are doing, you fall inside what this is somewhat called the triangle of frustration, because you cannot get it all. It all depends on knowing how to use the system exactly for the purpose of your experiment, and that's where we are also here to help. Just talk to your local expert on what are the best settings on the confocal for acquiring an image. If you do it, it'll tell you how to do it, right? And you can get images that look like this. So this is an example of a Z-stack, a series of images acquired at different planes of a myofiber. This is from William Roman at Edgar Gomes' lab at the IMM. These are all stacked together in this computer reconstruction. And you can see, so this is ex vivo. This is a myofiber extract from a mouse, and you can see all the different nuclei in the myofiber, and we can navigate through it, see, measure things where they are located, look at the desmin and tubulin distribution. So you're able to look at your sample in 3D. And in this case, you know, it is a slower acquisition, but you could also do this in live imaging and look at the nuclei moving with time. So this is just an example. So bottom line on the point scanning confocal, it scans your excitation spot on the sample point by point to build an image. So this means it's slow, really. It's not an image that you acquire all at once, as in a wide field. It typically takes 1 second to acquire an image, but this can easily increase if you're talking multiple channels with a high resolution image. With more pixels. The detection efficiency of PMTs is not very high, so only about 25%. So, you know, if you want to do live imaging with a point scanning confocal, it's not really the system of choice because of speed and because of the low detection efficiency and the high laser intensity that you need to use. These are all prone to photo bleaching and photo damage, so not really the best. Fortunately, there's a solution for this. Which are to use, instead of just one pinhole and scanning point by point, one at a time, to use multiple pinholes, scan multiple points in a sample, and use a camera for acquisition. And this is the idea behind the spinning disk confocal. So the spinning disk confocal, the whole idea basically is to multiplex the point detection on the sample. So the way it works is that you expand your laser light so it shines on the face of a disc. It hits a first disc with an array of micro lenses that will focus the laser light onto the second disc, which is the one that has the pinholes in it. And this one, of course, is placed in a conjugate focal plane as the focal plane of the objective. So these light coming from these pinholes will be focused in the focal plane of the objective. And because you have many of them, you will be exciting multiple points at once. Light that will be emitted by fluorophores at this point will be captured by the objective, go through the same pinhole. So here we are using pinholes for detection, for excitation, and for detection, similar to Marvin Minsky's design in that regard. So the emitted light will hit the dichroic, and because we are looking at multiple points and the disk is rotating very, very fast, we'll be able to generate an image. Let me explain to you in more detail how this works. So this is the pattern of pinholes on the disk. The distribution of the pinholes follows an Archimedean spiral, which is a trajectory that makes sure that precisely each point on the sample will be scanned, will be illuminated, and light from it will be collected only once as the disk goes through one rotation. So since the disk is rotating, all the points in the sample will be really very illuminated only once, really, really fast. And because it's so fast, you can even project this image, because it's now an image on a CCD camera. So let me show you, actually, this is from one of our spinning disks at the IMM. What I'm going to do is I'm going to stop the spinning disk, and you'll be able to see actually the pinholes. It's coming to a stop. You see it's decreasing its velocity. So here it is. So this is part of the disk. It's this part here. These are the multiple pinholes along the disk that will excite the sample. And then when I start rotating the disk again, you will see for a brief instant that at different points will be illuminated. So as the disk is spinning faster and faster, you will sample the whole image. You will be illuminating the whole field of view of your specimen, and this is an image that we can project on a CCD on a CCD camera. So with the spinning disk, we use multiple pinholes to scan the sample, so it's very, very fast. And you know, because we are doing this for a given field of view very fast, we don't need really a point detector. We can use a camera, a CCD or EMCCD camera that Telmu told you about in the last talk. So it's a high efficiency detectors that can go really from 25% of the PMT to 60, 70, 90% of light efficiency detection. And so the spinning disk is really great because it allows us to go fast and to be more sensitive, so to capture more light from the sample. So this means that we can reduce the laser intensity. All good things for live imaging. On top of that, it might even be better than the wide field illumination system because of the way that we illuminate the sample, which is not continuously. So each spot on the sample, each point on the sample is illuminated briefly for short intervals. This is also good for photobleaching because your electrons that will be undergoing the fluorescent cycle will not be continuously being excited and emitting photons, risking being photobleached by being just stripped away from the fluorescent molecule. This way of illumination in short cycles is actually better for preventing photobleaching. So spinning disk illumination detection is the most user-friendly for live cell imaging. So this is an example comparison between wide field and the spinning disk. This is a sample from Diogo Pagamos from Limassol Lab at IMM. So it's a mouse spinal cord stained with DAPI and UN. I've imaged it on a spinning disk, which actually has a double configuration. It's a spinning disk on the left port and the wide field on the right port. So you can easily appreciate that even though this is it's a thin sample. It's a 10 micron slice, but still on the wide field you get all of this blur, all of this fluorescence from planes above and below the focal plane, which you get rid of in spinning disk. And if we acquire a Z-stack for the sample in both modes, you clearly see the optical slice, the optical sectioning on spinning disk that's not occurring with wide field, and this is particularly striking when we look at the 3D reconstruction of it. I'm just now showing you the XZ projection. You see the way that the wide field illuminates, and you have basically fluorescence even when you are way even when you are far away from the plane where the sample is. The same thing doesn't happen on the spinning disk. So you know, even for a thin sample, if you're using a high NA objective, which is the case of this one, it's an oil immersion 40x NA 1.3 objective. If you need to do Z-stack, so the optical slice thickness of the sample is around 1 micrometer more or less. So even for a thin slice, if you need to do Z-stack, if you need optical sectioning, a spinning disk is much better than the wide field. The focus is much better than the wide field. Here's another striking example. This is studying data from, again, Niche from Lisa Figueiredo lab at the IMM. This is, you know, because it's so gentle for live imaging, you almost have no photobleaching. So these are Trypanosoma brucei parasites infecting hepatocytes. Here you can see it's a live movie, and even more striking, the next one. Same parasites, Trypanosoma parasites. This is intravital imaging, stunning data acquisition by Mariana Niche. So this is the Trypanosoma parasites in the blood flow of a living mouse. You can also see the heartbeat. This is done in looking at the blood vessel there. Look how fast the spinning disk can go. We couldn't do this on the wide field, of course. We wouldn't be able to even image a trypanosoma without the optical sectioning ability. You'd not be able to even resolve the detail and get the optical sections for this on a point scanning confocal. You could never go this fast, period. So the spinning disk is the ideal system for this. Having said that, there are now novel implementations of point scanning confocal that take place that take advantage of new detectors such as the Harry-Scan, which allows you to do excitation not point by point, but in lines of 4 or 8 pixels that can bring you closer to the acquisition speed of spinning disk, but we're not going to go there in detail. But just talking about the traditional point scanning versus spinning disk confocal. So spinning disk confocal is the best, right? It's the best confocal system that you want to use, except not necessarily, because you know the camera that you are using on the confocal, you might see it here. So it's the CCDs and the MCCD cameras that we use are typically limited to 512 by 512 pixels. In some cases, 1024 by 1024 pixels in order to be fast. So this doesn't necessarily match the optical resolution of the microscope. If you use a point scanner, you'll be able to acquire images with a much higher resolution. Also, on top of that, there is a disadvantage in using spinning disk, which is pinhole crosstalk. So, you know, on a point scanning confocal, we acquire an image of a sample point by point. On a spinning disk, we acquire multiple points at a time. Now, if your fluorophore is on the focal plane, it's emitting light. This light will be focused on the pinhole, on one of the pinholes of the spinning disk, and it will be imaged. It's fine. Now, if your fluorophore is further away from the focal plane, if it's at a given distance, what will be projected on that pinhole will be an autofocus disk of light. And as your fluorophore gets further away from the plane of the spinning disk, the autofocus disk grows, it gets bigger and bigger, until it eventually overlaps with adjacent pinholes. So this means that if you are further away, if you're really far away from a fluorescent probe in your sample that's emitting light, light from this sample will not be will not be fully rejected by the spinning disk, because part of it will go through the initial pinhole, but also through adjacent pinholes. Okay, so what this means is that, contrary to the point scanning confocal, where the further away you get from the focal plane, the less and less light goes through the pinhole, so that's how you achieve optical sectioning. On a spinning disk, there's a limit to this. Okay, there's a certain distance above which light will go through adjacent pinholes, and so you'll have a baseline transmission here that you cannot really eliminate. So the point being that autofocus rejection in the spinning disk confocal is not optimal for thick samples. The thicker your sample is, the lower your ability to do optical sectioning, because you're limited by this pinhole crosstalk effect. And so this might become a problem if you're looking at very, very, very thick samples, and you want to do really fine optical sectioning. Spinning this might not be an option there, or you might have a lot of still background and autofluorescent light that reduces your signal to noise ratio, which is what we want to increase in all image acquisition. So, okay, we have point scanning confocals, we have spinning disk confocals. Confocal is the best microscope of all. I have my bright sample perfectly stained. I want to capture the best image. I want to go to a confocal microscope. Is that the case? So I have a question for you now. Was this image acquired on a wide field or on the confocal microscope? I'll give you just a few seconds to think about it. This, by the way, is a real image. This was not photoshopped in any way. You can see there's a scale bar here. It's a real thing. The cells were really looking like this when Maria Henrique, João Ferreira, and I were looking at them at the microscope. So the answer for this is this image is not from a confocal microscope. This image is from a wide field microscope. And you don't have any autofocus light, because there is no autofocus light. The sample is very, very thin. It's just a monolayer of cells on the cover slip. So in case your sample is not thick at all, and what you are looking at is basically, even in this case, within the depth of field of your objective, where all of the cells look in focus, you don't need to go to a confocal microscope. Okay, you can basically see all the cells. You get a high signal to noise ratio because your sample is very thin. You have nothing above and below the depth of field of your objective, the focal plane of your objective. So this is a standard epifluorescence wide field microscope, which it's faster than the point scanning. It gives you very high, you can acquire images really fast, and also for live imaging is better than the point scanning. Not necessarily a spinning disk, but no, you don't need to go to a confocal all the time. And depending on what your sample is, we will tell you to go to different microscopes. Confocal is not the best for all experiments. There are also multiple ways to do optical sectioning. There's the point scanning confocal, the spinning disk confocal, which you've been talking about. I'm not just only going to briefly introduce multiphoton microscopy and light sheet microscopy, which I think Gabi will talk a little bit more in detail next Thursday. Also, structured illumination can be used for optical sectioning. So there are a variety of techniques. I'm just talking to you in this lecture about the more standard, more widely used point scanning confocal, spinning disk confocal, and now multiphoton and light sheet. So on a multiphoton microscope, we look at fluorescence, but we get fluorescence in a different way, rather than using a single photon excitation, which Telmo explained in great detail in the last talk. What we are going to do is to elicit the same photon emission from fluorophores by exciting them not with one photon, but with two photons. Okay, so this is one of those quantum mechanics effects where it's not really expected. But if, you know, in a very short amount of time, if you happen to have two photons with half, each one of them with half the energy of a single photon would need to have to excite this fluorophore, they will be perceived as one. They will be absorbed as one by the electron in the ground state, which will get excited in the same way and then lose energy due to vibration and rotation. Tom explained this, and then emit a photon in the same way. So the emission is exactly the same. It's the excitation that's different. This is a very rare event. Okay, it's very difficult to have emission, to have excitation by two photon, and it's so rare indeed that you need a photon density approximately 1 million times higher than what you have in traditional one photon absorption to generate fluorescence. This means that, you know, we're comparing here normal confocal excitation. Notice how the excitation of the laser, it goes through the whole sample, but it's focused here on the focal point, but we are still exciting above and below, hence the pinhole for getting rid of these fluorescence from planes above and below. On the multiphoton microscope, only really in the focal plane we have the optical density, the photon number high enough to produce this very rare event of two photon absorption and emission of normal fluorescence. So you can see this tiny spot here of two photon excitation. And now, it's still a scanning system, so it's a single point. So we need to move the point in the sample, and we need to acquire point by point, same thing as on the confocal. But now, because we are only exciting here in this spot, in this focal plane, this means that we don't need a pinhole. Okay, so whereas on a wide field we excite the whole field of view, it's very wide illumination, and we capture all the light that's coming from above and below the focal plane on the detector, and we get a lot of blur. On a confocal, we use a pinhole to reject. We excite preferentially just one spot in the sample, and we use a pinhole to reject the light coming from planes above and below. On the two photon, because excitation only occurs in this really femtoliter focus volume, very, very narrow, we can basically capture all the light that comes from the sample because we know it's coming from that point. So no pinhole, okay? And the detector is usually placed very close to the objective. It will not go through the scanning mirrors as on a confocal. It's not the scan detection, and we basically capture all the light that's coming from the sample, even that one that has been refracted, goes through different angles. Doesn't matter because we know it's coming from this point. So what's the advantage of this? The advantage is that by using photons that have half the energy, they will have twice the wavelength. We're talking about infrared light that can penetrate the sample deeper. So whereas in a confocal microscope, you're limited to, 100 microns, 150. If you look at some point absorption, refraction, means you'll not be able to excite your sample at higher depths. Also, the working distance of the objective is somewhat limited, and that in multiphoton, because you're using infrared light, which can penetrate much deeper, you can image way beyond what the confocal would usually image, which is this area around here, and go 50 microns, 60, 80 microns, even if you excite not with two photons, but further 3 photons, you can even go deeper and image almost 1 milliliter in your sample, and this is typically the technique of choice for imaging brains, mouse brain, particularly in mice brain in particular, because you can image the different layers of the brain and neurons as they in Z. So what's the downsides of this? Well, basically, the resolution of the multiphoton is not as good as that of the confocal. Okay, remember from David's talk that the resolution depends on the wavelength of light. So because we are using twice the wavelength, the resolution in X, Y, and also in Z of a multiphoton will be worse than that of a confocal. So you have optical sectioning. Okay, you don't have the light being detected above and below the focal point as you have here in wide field. Look at the point spread function of the wide field. You have optical sectioning on the multiphoton, but you don't have the same resolution of a confocal. So if you're imaging cells, 10 micron cells, don't go to a multiphoton, go to a confocal. If you're imaging brain slices, go to a multiphoton, because you'll be able to image much deeper. Okay, just a brief introduction. Am I doing on time? Okay, just a brief introduction to light sheet microscopy. Gabi will talk about it in greater detail. So basically all the microscopes that we've been looking at use epifluorescence illumination, meaning epi is from Greek the same. So it's actually the same lens, the same objective that is used to excite your fluorescent sample and to capture the light emitted by that sample. So this is it's the same lens that's used to illuminate and to detect light. On a light sheet microscope, this is done differently. So we're actually decoupling illumination and detection. We'll be using one objective to illuminate the sample, and the illumination is done by creating a light sheet using a cylindrical lens or other means, by moving a beam of laser also, for instance, in a plane. So we will be exciting the sample using a light sheet, a plane of light, and so this whole plane will be illuminated, and then detection will be performed by a detection objective placed orthogonally to the excitation objective. So we are using this one for illumination and this one for detection. So optical sectioning is achieved because we are only illuminating with the light sheet one plane at the image. And image acquisition is done by standard wide field detection. So we are acquiring an image with a CCD, CMOS, MCCD camera on this side. So acquisition can be very, very fast. We don't have light coming from planes above and below the focal point of the objective. The light sheet is, of course, placed at the focal plane of the detection objective. We don't have light coming from planes above and below because we are not exciting those planes. So that's how we get optical sectioning. Increased advantage is we also don't photo bleach and don't the planes above and below the plane that we are imaging because we are not exciting them. So you see in standard epifluorescence, wide field illumination, even you're focused here, but you're imaging all across the sample. Same thing in confocal, same thing in multiphoton. You're always imaging from not in multiphoton, sorry, multiphoton you only get that on the focal plane, but in confocal you image from top to bottom and use a pinhole to reject that. So you when you do a Z-stack, you are in fact photo damaging and photo bleaching your whole sample, your whole volume. On the light sheet you don't get that, so you only illuminate and you only get photo damage on that plane, and more detail on that on Gabi's talk. So bottom line, which microscope do you use? Well, it depends. It depends first if you have, this is, okay, of course you need to talk with us in detail to your local expert to understand what's the best system, but just as some guidelines for you to think about. So fixed samples that are less sensitive to light, you don't need to acquire that fast. They are typically mounted in fixative media that also have anti-bleaching, anti-quenching reagents. So bleaching is not really a concern there. If your sample is really thin and you're using a low NA objective with a big field of depth, meaning that everything will look in focus and you don't have, for instance, some planes above and below because the sample is very thin, then what you're going to use is a wide field. If you're using a high NA objective, with a much shallow depth of field. If you're looking, even if you're looking at cells, 10 micron cells, but you need to do Z-stack, and you need to resolve subcellular structures, then you go for point scanning confocal, because there you can get optical slice thickness of 900 nanometers or less, and you can get subcellular detail. If your sample gets thicker, between 20 microns and 100 microns, that's point scanning confocal classic usage period. That's where it's where it shines. It's fixed samples up to 100 micron. You get the highest resolution going for a point scanning confocal slower acquisition. Thicker than that, you need to go multiphoton or light sheet. And if it's really, really thick, like you're talking a whole zebrafish, then you go for a light sheet. If it's live samples that are very sensitive to light, you want to avoid photo damage and photo bleaching while imaging the samples, things change now. They get more complicated. Of course, you need to keep the sample alive in the microscope. That's the first challenge. But depending on what you're imaging, again, if it's a thin sample, a monolayer of cells using a low energy objective, just go wide field. Spinning this may have an advantage there, like I told you, because of photo bleaching and photo damage. It's more gentle even than wide field because of the way that you excite the sample. So it could be an option there. If you're using a high NA objective, then spinning disk for sure. For live imaging, you, as I shown you with your Paramus sample, you'll be able to section through your sample even for thin 10 micron samples. If you have a fixed sample between 20 and 100 micron, now it's a little more bit of a toss-up between the spinning disk and the point scanning confocal. It depends on what you want to do. If you want to image with a fast speed, with a high sensitivity to avoid photo damage, then spinning disk is your system. However, if you have a very fixed sample, if your fluorophores are not sparsely distributed in the sample, basically if you have a lot of fluorescence, then you might need the extra autofocus reduction that the point scanning confocal can give you. So here it will depend really on what you need to do. If the sample gets thicker, then of course you need to go to multiphoton or light sheet. And if it's really thick, again, light sheet is your option. Okay, so this was a very brief introduction to confocal and optical sectioning. I just want to thank the people at the IMM that give me the images or samples to image, William, Diogo, Mariana, and João Ferreira. Many of the illustrations that I've shown come from the Molecular Expressions Optical Microscopy Primer and versions of that from different companies. These are great educational websites with full detailed explanations, and I really encourage you to have a look at them. They are not only visually very, very beautiful, but they have a lot of knowledge. It's a very good starting point for beginners. And I'll take your questions. Thank you.
Thank you. Thank you, Rino. I think, well, there was one question, but I think you already answered it quite detailedly. That was about when to choose a wide field and when to choose a confocal microscope and what is thick and what is thin. I think you already answered to that. Are there any other questions? You can also use the raise hand option. Okay, Dinesh has.
Dinesh.
Hello.
Hello.
Hi. Am I audible?
Yes.
Yeah.
Yes.
Hi, Rino. It was a nice presentation. It's just a simple question. When we are doing the video with the camera and the resolution was not so clear as in the microscopy, what was the reason? While we are using the confocal microscopy to visualize the motion of the lymphocyte, that use lymphocytes, or you saw in the diagram, and it was little bit blur. So what was the reason? Is there some reason for that?
So you're
not so clear.
You're talking about the spinning disk comparing to the point scanning.
Yeah.
Yes, well, there are a couple of reasons. One is the camera, as you're mentioning. So the camera on the spinning disc is typically, and in our case, it's 512 by 512 pixels. So the same field of view on a confocal microscope, where you would acquire an image point by point to match the optical resolution of the microscope, you could easily acquire, or you would have to acquire with an optimal pixel size, an optimal frame size of 1 megapixel, even more. I can tell you little bit, but maybe 1800 pixels, something like this. So the resolution of the number of pixels of the image on the spinning disk,
So
because of
what is the good pixel or the choice of the camera that we can see without blurring as clear as it was in the image? What is
Well,
the option?
on a spinning disk, you get the one camera with 512 by 512 pixels, and you can also not change the size of the pinholes on the disk because they are fixed. So you're limited to that. On the point scanning confocal, you can choose the frame size. You can choose the number of pixels because you can choose the number of points that you're scanning in the sample. So it's much more versatile on the confocal, and you can match that to the objective and the field of view that you are using. So that's one reason why, because on a confocal you can really fine tune it, and on a spinning disk you're limited to the camera and to the pinholes that you're using. Another reason is, like I told you, that the optical sectioning, the autofocus ability to remove light is different on the spinning disk and on the point scanner, whereas it excels on the point scanner on a spinning disk for a fixed sample, and that was the case. That was intravital imaging, so the whole mouse was actually, the whole liver was filled with fluorescent cells. You still have light from planes that are not the plane of focus being detected in the spinning disk because of the pinhole crosstalk. So you'll have your signal to noise will also go down. Then again, because of speed, because it was a very, very fast movie, we're talking about exposure times of tens of milliseconds. And this brings down your signal to noise ratio a lot. So we are basically acquiring just a few photons, and what you're seeing that looks kind of a noisy image is because of the contrast enhancement that we are making. So we're amplifying the signal to get that to get the dynamics of it, to get the speed of it. It will basically be impossible to acquire on the point scanning. But remember the triangle of oscillation, you cannot have it all. So because of because you wanted speed and sensitivity there, resolution and resolution and sensitivity basically were compromised for the sake of speed of acquisition. So that's the reason why, because it was a very fast image with a very low exposure time on the spinning disk confocal, whereas the other one that I showed on the point scanner was, a very slow acquisition with an optimal frame size and a much larger total exposure time because the pixel dwell time of the laser was higher. So in one case we went for resolution, on the other case they went for speed.
Yeah, thank
I
you.
would like to contribute, if possible, on this, just with two things, guys. So the first thing, that what Rino said is all correct, but there is also one factor that might help to flexibly adapt the imaging that you can do at the spinning disk, and it's like choosing different magnification factors of your lens. So in fact, the magnifying factor in the lens is fundamental when you have like a detector, like a camera with fixed pixel size, because then changing the magnification factor, you change how much you, so how big is the image of your sample that you project on your chip. And this will increase the sampling factor and therefore the resolution until you might get eventually the optical resolution that is theoretically predicted with the Abbe formula. So this is a thing that is very important. It's not extremely important in confocal microscopy because in a single point scanner confocal, because as Rino said, you can flexibly adapt the number of pixels and the sampling factor. But if you have a camera-based system, then the magnification of the lens plays a crucial role. And there are also other magnifying factors that can be present in the optical path. So except the the lens, the objective lens, then there might be optovar lenses that can further magnify the image that if needed. Of course, this also implies like smaller field of view. So it depends, then it's again a compromise. So whether if you need to, you cannot have it all. If you need to image like a very large area very quickly, then you need to renounce necessarily to some of the resolution. Although nowadays there are systems that are equipped with scientific CMOS camera that provide like bigger chips with better resolution. And then the second thing that I would like to say is actually for all of you guys, also for like my colleagues, the heads of the other facilities that might not know this. And it's related with the history of spinning this microscopy invention. It's very quick. So I will share my screen for this if possible. I don't know if Rino needs to...
Stop sharing.
Can do it. Okay. So share. So this is the original patent, so the scheme of the original patent of spinning this microscopy that was actually filed in 1966, it's actually filed in 1967. And you have to know that the inventors of spinning this microscopy are these two guys. So Petran and Adrashki. So Milan Andrasky was still in alive. I think it's still alive last time that I visited Czech Republic, and they are both from Pilsen in Czech Republic. So Mojmir already died like a few years ago. So these two guys, so they invented and patented the spinning disc in Pilsen, which is famous for beer, but now you know not only for beer, also for the spinning disc, and almost nobody knows about this because of the Iron Curtain, so that divided the world after the Second World War. So basically for the people living in Czech Republic, the map of the world was looking like this. So nothing after the Czech Republic border with Germany. So there was really like, it was forbidden like almost any exchange. And if you go to Wikipedia and try to check for like the invention of spinning disc invention, you will see that Yokogawa invented in the 1990s the spinning disc, but it's not the spinning disc that they invented. That they use the patent of Petran and Adrasky, and what they invented is the microlens arrays. So that are positioned in correspondence of each pinhole of the spinning disc, and that increase the intensity of light with which the sample is actually excited. But these two guys are those who truly, so who are the fathers of this technology. So that's it. I wanted to give this historical contribution because it's something that people might not know. And I was exposed. This picture was actually taken at the Max Planck Institute where I was working in Dresden when we invited these two guys like a little bit more than 10 years ago. Now I will stop sharing. That's it.
Thank you, Larry.
Thank you. And we have one last question. So Inez is asking, how can we measure the transparency of a sample before doing the light sheet microscopy?
So I saw this question, but I will leave this question, if you agree, guys, for the next session of webinar for Thursday, because Gabby might have a lot to say about this when he will also talk about light sheet microscopy and clear
and tissue
samples.
Clearing. Yeah.
Exactly. So follow us. Don't forget about the second appointment, and then there will be like further explanations and in-depth explanation of this topic on Thursday.
Yes, sorry, Inesho, you will have to wait until Thursday. So yes, please join us again at the same time in 2 days on Thursday to hear more about super resolution, high throughput microscopy and screening, and mesoscopy, large scale imaging, and tissue clearing.
Okay. Thank you all, guys.
Thank you, everybody.
Thank you.
Thank you, and see you on Thursday. Bye-bye.
See you Thursday. Bye-bye.
Thursday.